ओके बेटा, तो let us start the topic, that is classification of crystalline solids. तो क्रिस्टलाइन सॉलिड जो है क्या होते हैं और वो एमॉर्फस से कैसे डिफरेंट है वो हम लास्ट लेक्चर में कर चुके हैं. So amorphous substances, they have short range force order, right? But in crystalline solids there is a long range order, and you know most of the substances are crystalline in nature. जैसे जितने भी metallic elements हैं, iron, copper, silver, all metals. Non-metallic elements like sulfur, phosphorus, iodine, and ionic compounds like sodium chloride, zinc sulfide, even organic compounds like naphthalene, they form crystalline solids. And crystalline solids, there is long range order. In crystalline solid, there is long range order, but in amorphous solid, there is short range order. Now, crystalline solids can be classified in various ways. Like method depends on the purpose in hand. Like we will classify crystalline solids on the basis of nature of intermolecular forces or intermolecular forces और the bond जो constituent particle के बीच में होते हैं, atoms के बीच में, ठीक है. तो पहला है van der Waals forces, ionic bonds, covalent bonds, metallic bond. तो ये जो bonds हैं इनके बेस पे we can classify crystalline solids into 4 categories. First is molecular. In molecular crystals, molecular solids, there is van der Waals forces of attraction. Molecules के बीच में क्या कैसा attraction होता है? van der Waals forces of attraction. और जो ionic solids होते हैं उनमें क्या होते हैं? Ionic bond. There is electrostatic force of attraction between the ions. And metallic solid, तो metallic solid में क्या होता है? metal के जो आयन होता है उसको बोलते हैं बेटा कर्नल, और उसका जो है कर्नल मीन्स पॉजिटिवली चार्ज्ड आयन, लाइक सोडियम का कर्नल बोलेंगे तो सोडियम पॉजिटिव, एंड इलेक्ट्रॉन्स, फ्री इलेक्ट्रॉन्स. सो उनमें जो अट्रैक्शन होगा डीलोकलाइज्ड इलेक्ट्रॉन और कर्नल के बीच में उसको बोलेंगे metallic bond, or that type of solid is called metallic solid. And last category is covalent solids, जिनमें क्या होते हैं? covalent bonds, generally non metals के बीच में होते हैं और उसको बोलते हैं covalent solids. So इनको हम अलग अलग कैटेगरी को एक एक करके करते हैं. So first is molecular solid. तो molecular solid, as the name suggests, molecular solid में जो constituent particles हैं वो क्या होंगे? Molecules. Molecular solid में जो constituent particles क्या होंगे? Molecules. और आपको पता है molecules non polar हो सकते हैं, molecules polar हो सकते हैं, and third category is special category, that is hydrogen bonded. ठीक है. So first is non-polar molecular solid. तो non-polar molecular solid जो है उनमें होंगे तो या तो एटम्स होंगे जैसे आर्गन है, हीलियम है, या फिर मॉलिक्यूल्स होंगे जिनमें नॉन पोलर कोवेलेंट बॉन्ड्स होंगे जैसे H2 है, Br2 है, Cl2 है, इवन CCl4 है, CO2 है, ये भी कैसे मॉलिक्यूल है? CO2 कैसा मॉलिक्यूल है, पोलर या नॉन पोलर? वेरी गुड, हाउ डू यू नो, कैसे पता चला? बिकॉज इन CO2 बॉन्ड्स कैसे हैं CO2 में, बताओ CO2 में बॉन्ड्स कैसे हैं? CO2 में बॉन्ड्स कैसे हैं, पोलर या नॉन पोलर? CO2 में देयर आर पोलर बॉन्ड्स बेटा. CO2 में actually CO2 is like this. So in CO, oxygen is more electronegative than carbon. So polarity is towards oxygen. On the other side, again polarity is towards oxygen. Therefore, net polarity is 0. Both bonds are polar, but because of its symmetrical arrangement of bonds, polar bonds, the net dipole moment is 0. That's why CO2 is non-polar. Same is the case with CCl4. In CCl4, there are 4 polar bonds, but due to the symmetrical arrangement of these 4 polar bonds, net polarity of CCl4 is 0. So all these molecules are non-polar covalent bonds. And you know, in non-polar molecules, there is symmetrical distribution of electrons, or we can say charge. There is symmetrical distribution of electrons or charge. That's why there van der Waals force of attraction, and that's why they are called non-polar molecular solids. The category is called non-polar molecular solids, and these van der Waals forces in non-polar molecules especially, that is called London force, because it was discovered by Fritz London. Okay, it is also called dispersion force, and they depend upon size, molecular mass, number of electrons. And this way, if size increases, van der Waals attractions increases. Molecular mass increases, again it increases. That's why if we compare helium, neon, argon, krypton, xenon, so xenon is a xenon, if it is a solid, if it forms in the form of solid, then melting point of xenon is more than krypton, than argon, neon, helium. Although they are gases, but at very low temperature and high pressure, they can be made as solid. And if we compare the melting point of these solids, See, these are novel gases. We can make them solid by lowering the temperature and increasing the pressure. And if we compare the melting point, then so xenon has highest and helium has lowest, because as van der Waals attraction increases, melting point increases. But you know, van der Waals attractions are weakest. That's why most of the time we write weak van der Waals attraction. And because of weak van der Waals attraction, these solids are soft. And at the same time, because they are molecules, so in molecules electrons are tightly held, electrons are not free to move. That's why they are always non-conductor of electricity. The melting point is low, we have already discussed, because there are only van der Waals forces of attractions, and which are weak attractions, and they are usually liquid or gaseous state at room temperature and pressure. That's why I said, to form non-polar molecular solid, we have to lower the temperature and we have to increase the pressure. Otherwise, at room temperature and pressure, because of weak attractions, they are generally gases, and sometimes some are solids. Sorry, some are liquids. Okay. Now, polar molecular solids. So, molecules of the substances like HCl, SO2, they are formed by polar covalent bonds. Now, polar covalent bonds, see, in HCl, you know, H is less electronegative, so it acquires partial positive, and Cl is more electronegative, so it acquires partial negative. And direction is towards Cl, H plus, Cl negative. Same is the case with SO2. It's like this. So again, both are polar. So in polar molecules, there is dipole-dipole attraction, because there is separation of charge, and therefore positive end attract negative end of the other molecule, and negative end attract positive end of the other molecule. In this way, there is dipole attraction, somewhat stronger than London forces, or we can say dispersion forces, but they are not very strong. So molecules in such solids, they are held together by strong dipole-dipole interactions. They're but they're not very strong, as I told you. So they are again soft and at the same time non-conductor of electricity, because electrons are tightly held and their melting point is somewhat higher than those of non-polar molecular solids. Again, most of these are gases or liquids under room temperature and pressure. Solid SO2, solid ammonia, there are some of the examples, but ammonia is also under the heading of hydrogen bonded molecular solid, because when hydrogen is attached to FON, when hydrogen is attached to FO or N, then those molecules form hydrogen bond. Okay, and you know, hydrogen bonding is stronger than even dipole-dipole attraction. Actually, hydrogen bonding is a special case of dipole-dipole attraction. But because atoms involved, they are highly electronegative, therefore magnitude of the charge developed is more, and that's why hydrogen bonding is stronger. Okay, so see, the molecules of such solids contain polar covalent bonds between hydrogen and phone. I remember it as phone, but phone is FON, atoms. So strong hydrogen bonding binds these molecules of such solids like H2O in ice, even ammonia, HF, and they are again non-conductor of electricity. Generally, they are volatile liquids or soft solids like ice is a solid. Soft solids under room temperature and pressure. Okay. Now, ionic solids. Ionic solids, the constituent of ionic solid are ions, cations, and anions. So, in such solids, cations and anions, they are arranged in three-dimensional network. See, okay. So, NaCl crystal, I'm going to draw. Like if there is Cl negative, then here it is Na positive, Cl negative, Na positive, Cl negative, Na positive, Cl negative, Na positive, Cl negative, positive, negative, positive, negative, positive, positive, negative. In this way, we have to arrange the ions. Okay, so this is 3D arrangement of NaCl crystal. So in ionic solids, cations and anions are arranged in 3D structure, and therefore there is a strong electrostatic force of attraction. See, such solids, they are formed by three-dimensional arrangement of cations and anions, which are bound by strong electrostatic forces or Coulombic forces. That's why these solids are hard and at the same time brittle in nature. See, solids, these solids are hard and brittle. Brittle means they can break easily. How do it possible that strong attractions are there and they break easily? Because when we apply shearing force, what happened? One layer slip over the other, and that's why similar charges come close to each other. See, positive, negative, positive, negative. Here negative, positive, negative, positive. Like this. Now, when we apply the shearing force, what happens? They move. When they move, this positive end moves to positive, and this here negative end moves to next negative, positive in this way, and the one here which is negative that comes here. So similar charge come close to each other, and in this way there is a attraction that become same type of repulsion. So strong force of attraction changes into strong force of repulsion because like charges come close to each other, and that's why they break easily. That's why they're hard but brittle. And as attractions are strong, so they have high melting and boiling point. Now, there is a 3D arrangement of cations and anions, and they are tightly packed. They are not free to move. So that's why ionic solids, though they have ions, but in solid, as ions are fixed, they are not free to move. So they behave as insulator. See, since ions are not free to move about, they are electrical insulators in the solid state. But in molten state or when they're dissolved in water, ions become free to move about, and therefore they conduct electricity. That's why they conduct electricity. In molten state or when dissolved in water, the ions become free to move about, and that's why they are good conductor of electricity. So the question comes, okay, why ionic solids are insulators in solid state but are good conductor of heat and electricity in molten state or in aqueous solution? Then you can say that in solid state ions are not free to move, they occupy the fixed positions, and that's why they are bad conductor of electricity, and they behave as electrical insulators. But in molten state or when they are dissolved in water, ion become free to move about, and that's why they conduct electricity. Now next, metallic solids. Now when we talk about metallic solids, you know electron C model metal, if it is a metal piece, kernels occupy the fixed positions. In metals, kernels occupy the fixed positions, and electrons are free to move. Electrons are free to move. So these kernels, positively charged ions, these positively charged ions are called kernels. So metals, they are orderly collection of positive ions surrounded by and held together by a sea of free electrons, and that's why it is called electron sea model. There is a sea of electrons. Electrons are free to move, and kernels occupy the fixed. Electrons are mobile and are evenly spread out throughout the crystal, and each metal atom contributes one or more electrons towards this sea of mobile electrons, depending upon the valency. Like sodium contribute one electron, but magnesium contribute two electrons. That's why kernel of the sodium is Na plus, and kernel of magnesium is Mg2 plus. Kernel of aluminium is aluminium 3 plus, and there are three valence electrons. So these free and mobile electrons are responsible for high electrical and thermal conductivity of metals. So metals are good conductor of heat and electricity. They are good conductor of electricity as well as they are good thermal conductor. They can conduct heat as well. So when an electric field is applied, these electrons flow through the network of positive ions, and that's why they are good conductor of electricity. But when we heat it, if we heat one portion of the metal, you feel the temperature or hotness in the other part also. So that means, because when heat is supplied here, these electrons gain energy and they move towards other end. And they move towards other end, the high energy electrons can take a position here only, and that's when they spread the thermal energy uniform. So thermal energy is uniformly spread throughout by the free electrons. And another important characteristics of the metal is their lustrous property, shining and color in certain cases. This is also due to the presence of free electrons in them. Because electrons are free, therefore visible light can excite them. The higher level, when they fall back, energy is released corresponding to some color sometimes. That's why they are colored and shining, because they emit light. When excited electron comes back to the ground state. And metals are highly malleable and ductile. What do you mean by malleable? They can be beaten into sheets. Ductile means they can be drawn into wires. That is the property of metals. Now, covalent or network solids. So, crystalline solids of non-metals, they result from the formation of covalent bonds between adjacent atoms throughout the crystal, and these are called giant molecules. We call them as giant molecules because there is a network of covalent bonds. There is no single covalent bond. There is a network, like in diamond. There is network of covalent bonds. And covalent bonds, they are strong at the same time direction in nature, and that's why atoms are held very strongly at their positions, and that's why these solids are very hard. They are not brittle. By mistake it is written, I think. Such solids are very hard but not brittle, and they have extremely high melting point because we have to break the series of covalent bonds. That's why they're very high, and they may even decompose sometimes before melting. They are also insulators and do not conduct electricity. But some, like graphite, that can conduct electricity. There are a few exceptions, but most of them, they are insulators. Like diamond, silicon carbide, they are typical examples of the solids. It is written graphite. It belongs to this category, but it is soft at the same time a conductor of electricity. And its exceptional property is due to its structure, because there are layered structures. See, first layer, second layer. In between the layer, there is van der Waals attraction, and therefore one layer can slip over the other. And within the layer, there is one electron free per carbon, and therefore they conduct electricity within the layer. Right? First layer can conduct here only, second layer, third layer, because there is van der Waals attraction. One electron free electron from one layer cannot move to the another, but they can conduct electricity within the layer. But in diamond, like this, each carbon is forming 4 covalent bonds, therefore there is no free electron. Here carbon is sp3 hybridized, but in this case, carbon is sp2, and 1 electron is free per carbon. See, carbon atoms are arranged in different layers, and each atom is covalently bonded to 3 of its neighboring atoms in the same layer, and therefore fourth valence electron of each carbon atom is present between different layers and is free to move about, and these free electrons make graphite a good conductor of electricity, and different layers can slip over other, and this makes the graphite a soft solid and good solid lubricant, because they can slip over each other. That's why they are good lubricant. So different properties of the 4 types of solids, they are listed like this. First is molecular solid. There are 3 types: subtype non-polar molecular solid, polar molecular solid, hydrogen bonded molecular solid. Constituent particles are molecules only. In non-polar, there is dispersion or London forces. In polar, there is dipole-dipole attraction. In hydrogen bonded, there is hydrogen bonding. Example are given: argon, CCl4, H2, I2, CO2. They are all non-polar molecular solids. HCl, SO2, dipole-dipole attractions are there. H2O, ice, hydrogen bonded. They are soft, and somewhat hard. Hydrogen bonded is somewhat hard. They are all insulators. They are very non-polar molecular solids. Weak van der Waals forces, dispersion forces, weakest van der Waals attractions are there. Therefore, their melting point is very low, and polar and hydrogen bonded, they are also low, but higher than non-polar molecular solid. In ionic solid, constituent particles are ions. Ions means cations and anions, and they are arranged in 3D, and there is Coulombic or electrostatic force of attraction. Examples are NaCl, MgO, Zn, and CF2. They are hard but brittle. And insulators in the solid state, because in solid state ions are fixed, they are not free to move, but in molten state or aqueous solution, they behave as conductors, and their melting point is high. Metallic solid. Constituent particles in metallic solid are positive ions in a sea of delocalized electrons. Positive ions, they are called kernels, and bonding in them is metallic bonding. Iron, copper, silver, magnesium, even sodium, all the metals are in this category. Hard, at the same time malleable and ductile. Hard, but malleable and ductile. They are conductors in solid state as well as in molten state. Their melting point is fairly high. Covalent or network solids, why they are known as network solid as well? Because there is network of covalent bonds. That's why it is called network solid. There are atoms, covalent bonding. Examples are SiO2, quartz, silicon carbide, carbon in the form of diamond, aluminium, nitride, even graphite. They are all hard, but graphite is an exception, that is soft. They are all insulators, and they have very high melting point. And graphite, it is conductor, soft as well as conductor. That is an exception that I know, that I tell you just now, that in graphite per carbon atom there is one free electron, and therefore there are delocalized electrons within the layer. Therefore, in graphite hexagonal layers, they conduct electricity within the layer. Those delocalized electrons conduct electricity within the layer. So that's all about this topic.